In today's video, we are going to study about cyclic structures of carbohydrates. Carbohydrates, they don't exist as, straight chain structures the way we have been used to. So they exist as cyclic structure, and the reason being they exist as cyclic structures are there are certain evidences, like for example, glucose. It does not form the bisulfite compound that a straight chain carbohydrate should form. It does not restore the color of Schiff's reagent. It shows property of mutarotation. I'm going to make a video on mutarotation. And glucose should have reacted, the aldehydic functional group should have reacted with two molecules of, methanol, but it reacts with only 1 mole of methanol. So there are many such evidences which show that this glucose or fructose may not exist in straight chain form or the Fischer projection formula. So they exist in cyclic structures, and these are in the form of Furanose structure and Pyranose structure. Okay, so Furanose and Pyranose names have arrived from the structure furan. Furan is five-membered ring with a oxygen atom, heterocyclic compound, and pyran is a six-membered ring with a heterocyclic with a heterocyclic oxygen. Okay, so depending based on these two structures, we name these structures as pyranose and furanose. Here in today's lecture, we are going to study furanose pyranose structures of glucose. So what exactly happens here is in aldoses our functional group is aldehyde functional group. So there are reactions of aldehydes where aldehydes and the ketones react with the alcohol to form, and now when I'm reacting an aldehyde, it forms an hemiacetal. So this H goes with the oxygen, and this carbon and oxygen forms a bond. So this is called as hemiacetal. Because it reacts from aldehyde, we call it as hemiacetal. And when a ketone reacts, we call it as hemiketal. So this is the structure of hemiketal. Okay. That is why we say that they form six-membered and five-membered cyclic hemiacetal and hemiketal rings. If aldoses, we are talking about aldoses because the aldehyde group is present on first carbon atom. To form a five-membered or a six-membered ring, it reacts with C4 and C5 carbon. And ketosis, the keto functional group is present on the second carbon atom. So to form five and six-membered ring, it reacts with fifth and the sixth carbon atom. Now, at first place, why the reaction takes place? The reason is this carbohydrate rings, for example, glucose. This is glucose, okay? So these are not exactly straight as they look here. They are in C shape. The reason for them being in C shape because of the tetrahedral nature of the carbon. And now because they are in C shape, so this is alpha, beta, gamma and delta. This is your functional group. Carbon atom attached to functional group is alpha carbon atom. So this first carbon atom, your functional group is closer to the gamma carbon atom or the delta carbon atom, and that is why because of the C shaped type of structure, no, the aldehydic group and the OH group, they are close to each other, and the reaction takes place, and hence you get a cyclic structure. And because of this cyclic structure, what happens is, for example, let's take formation of a six-membered ring. So this is first carbon, second carbon, third carbon, fourth carbon, fifth and sixth. To get a six-membered ring, we have to react aldoses between first and fifth carbon atom. So the H of this will react with the oxygen to form OH. Okay, and this carbon will form a bond with this oxygen. So here there is a formation of, this was the oxygen which was present over here. This is a formation of oxide ring. Now here I have placed the OH group on the right hand side. The other possibility is the same reaction can take place where the OH group goes on the left hand side. So I'm not writing the oxide ring right left, I'm just placing this because this whole ring is planar. So here we have written the OH group on the left hand side. Now this was the first carbon atom which was initially achiral, Now it has become chiral. So new asymmetric center is generated on the first carbon atom at the functional group, and this is called as anomeric carbon atom. So this is your anomeric carbon, and these two are anomers. The new structures formed are called as what? Anomers. And on this anomeric carbon atom, when the OH group, this is a newly formed chiral center, when the OH group is on the right hand side, we call it as alpha anomer, and when the OH group is on the left hand side, we call it as beta anomer. So in glucose, there are two anomers, alpha and beta. Similarly, for other carbohydrates also, we have alpha and beta anomers. Okay, so glucose can be converted into alpha anomer, and like it shows two anomers, alpha and beta anomer, and how these anomers are formed, that is what we are going to see now. So Haworth projection formula is the cyclic structure, and the Fischer projection formula is the straight chain structure. So when we write a straight chain, so this is your aldehydic, six carbons. You can start writing like this: one, two, three, four, five, six. Okay, I'll write this first here. Uh, Wait. Hmm. I'll write the glucose structure over here. Fischer projection formula: two, three, four, five, six. You can first write the six carbon atoms. Okay. Now, this is the straight chain of glucose. You know how to draw the structure of glucose. Watch my first video. Placing the OH groups on the right, on the proper sides are very important. Otherwise, they give you a completely different carbohydrate. We want a Pyranose formula. Pyranose is six-membered ring. This is your pyran, so six-membered ring. So to get a six-membered ring, the reaction has to take place between, cyclization has to take place between first and the fifth carbon atom. So when the reaction cyclization takes place between first and fifth, let's draw the oxide ring between first and fifth carbon atom. Okay, same thing you can draw over here. Now, first I'm showing you like this on a in a straight format, and then we will show how the rotation is taking place. When it goes on right hand side, you get alpha anomer. When the OH goes on the left hand side, we get beta anomer. Okay, so this is your anomeric carbon atom now, and rest of the structure of the glucose remains same. So I'm not drawing that structure right now. Okay, or wait, I'll draw it quickly. Okay, just write, just draw exactly same structure as the straight one. This is Fischer, and this is now Haworth. Now let's see how to draw the exact structure and how to name them. Right now, once you know this structure, let's draw this. Let's show the rotation now. Now this same straight chain, as I said, it is C shape, right? So let's draw it in a proper orient, let's orient it in a proper way. So I'm trying to draw the C-shaped structure. So you can start with the carbonyl group as well. So this is the carbonyl group. So first let's number it: 3, 4, 5, and this is your sixth carbon atom. What is there on the first carbon atom? Aldehyde group. Okay, what is on the second carbon atom? Now second carbon atom, OH is on the right hand side. Now you should follow this rule. When OH is on the right hand side, all the groups on the right hand side, they go below the plane of the ring, or you can write it down. And when the groups are on the groups on the left hand side, you are going to write it up. So where is this OH group on the second carbon atom? Right hand side. Right hand side means it will go down. So for this, let's begin from this structure only. For third carbon atom, where is the OH group? On the left hand side. So let's write it up. For fourth carbon atom, OH is on the right hand side. Fifth carbon atom, OH is also on the right hand side. And this I have written here like this. Okay. Now we want a reaction to take place between fifth carbon atom and first carbon atom. So if you look at this, they are not quite close to each other. So let's orient the sixth carbon atom so that the structure looks better, or orientation, after orientation bond formation will be easy. So I need to bring this OH over here. So I will rotate this group over here. This group goes over here. This group goes over here. Okay. So when we draw orient this, what we will do is we will write CH2OH on the top. Okay, we are doing this without change in the stereochemistry. Okay, OH comes over here, which is now much closer to your C double bond O group. Rest of the structure remains exactly same. Okay, so this was fourth carbon atom, OH down, H up, H down, OH up, OH down, H up. This is the carbonyl group that we were talking about. Uh, Now your reaction will take place over here. Okay, so this will attack, the bonds will shift over here, and this OH will go here and form a bond with oxygen, and this gives rise to two structures. Now which are the two structures? One is the alpha ionomer and the other one is the beta ionomer. So to draw that, first we will draw the six membered ring this way. Okay, next what you will do whenever you are drawing these structures, now this is, you can follow this system. Draw the six-membered ring, put the bonds, put the position so that it becomes easy for you to write the whole structure. The first carbon is anomeric carbon atom, which is denoted by this symbol. Now there are two possibilities. OH will go down, okay, on the first carbon atom. The rest of the structure remains the same. Okay, so rest of the structure remains same. Sometimes H is also not drawn. We just show OH up, down. That is also enough. This is which ionomer? Alpha ionomer. The reason for it is alpha because OH is down. Okay. What is the other possibility? Draw first the six-membered ring properly. Show the bonds. Okay. Number it. This is your anomeric carbon. We have drawn the alpha ionomer. Let's draw the beta ionomer. Beta ionomer, OH is up. The rest of the structure is exactly same. Okay. Fine. So this is beta. Now how to name this? This is called as alpha because we are talking about D-glucose. So alpha D-gluco, and this is the pyranose structure. Pyran, no? Six-membered ring. And this is called as beta D-glucopyranose. Okay. This is how you get. So C1, sorry, C1 carbon atom, for C1 when OH is up, we call it as beta ionomer, and when C1 carbon atom OH is down or below the plane of the ring, we call it as what? Alpha ionomer. This was the pyranose structure, and always remember for pyranose structure, for pyranose, that is six-membered ring, six-membered ring, the bond formation takes place between C1 and C5. And for Furanos structure, it will take place between C1 and C4 4 carbon atom. Okay, so let's go for the Furanis formation of the D-glucose. Now, those who, if you people have understood this, it is now very easy to draw the whole thing. So again, let's draw the open chain form of the glucose so that you will understand. So you can start with one, two. Always draw first six carbon atoms. Okay, number the carbon atoms. 4, 5, 6. I told you to remember G. Okay, so OH, this is G, right? Oh, this way you can remember G. Hmm? Watch my first video. Now, Furanos ring formation between C1 and C4. Okay, that is how it will give you Furanos structure. Okay, so now this is first carbon atom and fourth carbon atom over here. Okay, because of the bent structure. So let's first draw again straight carbons in a straight line. You know the reaction is taking place between C1, 2, 3, 4. Okay, so first draw the cyclic ring between C1 and C4. Then you can put the OH on the first carbon atom, right, left. Here it is on the right. Here I am putting it on the left hand side. And let me first complete this. Fourth carbon atom, choose a fourth carbon atom. This is your fourth carbon atom. Show the oxide ring. Okay. And rest of the structure is same. I'm not drawing that now. Okay. So this is my alpha ionomer because my OH is on the right hand side. This is my beta ionomer because OH is on the left hand side. And this is the anomeric carbon atom. Now let's draw the Haworth orientation and everything. So we will show the C shape glucose. So exactly like the first one, you will draw this structure. So this is your first carbon atom, first carbon atom. Second carbon atom, as I told you, whichever groups are there on the right hand side will go down, whichever group are on the left hand side will go up. Okay, this way you will find it easy to draw these structures. You don't have to mug up these structures. Now remember, we are going to form a ring between which carbon atom? uh, First and fourth. So we need fourth carbon atom and first carbon atom to be close to each other. So the orientation that we have to do is on the fourth carbon atom. Now we need OH should be closer to this, so we need to bring OH over here, and this will be considered as the whole group which is getting oriented. So this whole thing gets oriented over here, H comes over here. Okay, so after orientation, what will be formed? Let's orient it first. So here you get, see, let's write first the C, that is the fourth carbon atom. Then you can go, you can go for the third, second, and this is your first carbon. So first carbon, what is there? Aldehyde group. Now fourth carbon atom, we have oriented this whole group, no? So we will write this whole group together over here. So CH2OH. Now you can place this OH over here just like the one in the straight chain. What is this here? OH, which is now close to your, and H is over here. Close to, close to your aldehyde functional group. So now the attack of the electrons, shift of the electrons, and then this OH will go and form a bond over here. So here it gives you now two structures. We are drawing the Furanos. Remember, Furanos is five-membered ring. So first draw this type of five-membered ring. Okay, then number the positions, one, two, three, four. Okay, draw the bonds. Now on the first carbon atom is your anomeric carbon atom. What is on the first carbon atom? If OH goes on the top, you will get beta ionomer. OH can go down, which will give you the alpha ionomer. Second carbon atom, look at this second carbon atom. Where is OH present? On the right hand side, down. Third carbon atom, where is OH present? Left hand side, up. Fourth carbon atom. Now fourth carbon atom was, what is it having? Fourth carbon atom, you can see over here, it is having H. Now H will stay below, okay, and this whole group will be above. So OH, H, CH2OH. Similarly, you can draw the alpha form. I have drawn the beta. So this is 1, 2, 3, 4. Okay, 1, 2, 3, 4. Always follow this pattern. We have drawn the beta ionomer. We'll draw the alpha ionomer. First, always go for the anomeric carbon atom because the rest of the structure is same. This is OH, H. This is COH, H, CH2OH. This is your sixth carbon atom. This is your fifth carbon atom. This is your Furanose structure. So how are we going to name this? This is alpha D glucofuranose, and this is beta D glucofuranose structure. This is your Haworth projection formula. This is how the orientation and everything takes place. And what we are doing here is we are reorienting or reorientation of the group at C4. 4 carbon atom. We are reorienting C4 carbon atom, whereas in Pyranose structure, we are reorienting which carbon atom? C5 carbon atom. This is how the formation is shown from Fischer to Haworth. Okay. Always remember for Pyranose, it is between C1 and C5, and for Furanose, it is C1 and C4. I hope you have understood this. Next video will be on why beta anomer is more stable than the alpha one for glucose. Okay, do watch. Thank you.